This is Group33's Fluids in Motion Project 2025. My name is MECN2022.
Hi, my name is Sanisiwe Zabi.
My name is Anderson Moni.
My name is Catherine Rodley.
My name is Hassan Mdab.
And my name is Jason Johnson.
The following apparatus is designed to replicate the contraction flow system described in the above theoretical problem. The first component is a 5-liter bucket acting as a constant head reservoir to supply water at a steady flow. Near the base of the reservoir, an outlet was drilled to fit the 22mm PVC pipe that serves as the main flow channel. A metallic reducer is installed along this pipe to form a contraction section, where the cross-sectional area decreases and the flow velocity consequently increases. Downstream of the contraction, the pipe returns to its original 22mm diameter, creating an expansion region where flow deceleration occurs. Finally, the discharged water is collected in a 1-liter measuring jug placed at the outlet. This enables us to verify the volumetric flow rate by timing how long it takes to fill the jug.
A U-tube manometer was constructed using glycerine as the working fluid. The glycerine was dyed red for visibility reasons. The height difference observed in the manometer reading represents the pressure difference between the static pressure at point 1 and the stagnation pressure at point 2. A surface thermometer was used to measure the temperature of the water, as temperature directly influences the density of water and consequently the accuracy of the results. A bent plastic straw was inserted facing the oncoming flow at point 2 to measure the stagnation pressure. Since point 1 serves as the static tap and point 2 as the stagnation tap, the setup effectively functions as a pitot-static tube, allowing for the determination of flow velocity based on the pressure difference between the 2 points.
Water is supplied from a reservoir into a pipe with varying diameters. The continuity equation is applied to show that velocity increases in the 15mm narrower pipe, maintaining constant flow rate. Bernoulli's principle explains the pressure drop during contraction and pressure rise during expansion. A U-tube manometer using glycerine as the manometric fluid measures pressure difference using hydrostatic pressure. At the stagnation point created by a straw facing the flow, velocity drops to 0 and pressure rises, allowing estimation of velocity using stagnation pressure principle. Finally, flow rate is calculated by measuring the volume of water collected over time.
Following this introduction, we will conduct an experiment to demonstrate how frictional and minor losses affect the performance of a fluid flow system. 2 experimental runs will be performed to help validate our findings. After completing the experiment, we'll run a Flownex simulation that replicates our setup. This simulation will allow us to compare the theoretical, experimental, and simulated results and evaluate how closely our experimental data aligns with theoretical predictions.
We make use of the hose pipe to let water fill into the bucket, which is acting as a reservoir for the system.
As we were filling the water inside the bucket, we had to make sure that the open end of the pipe had to be closed to ensure that the water does not flow out as we're trying to fill up the bucket. Once the water had reached a certain level in the bucket, we then allowed the water to flow out of the pipe. We let the water free flow for a short period of time to make sure that we get a steady flow and that the flow rate coming into the system is the same as the one going out of the.
Once the pressure begins to change, you will then note the change in height in the manometer fluid.
We then used a 1-liter measuring jug and a timer to measure how long it would take for the water to fill up the measuring jug. Once the water had filled up the 1-liter measuring jug, we then stopped the timer and the values were then recorded. These values are going to be used to find the flow rate of the system.
During the experiment, we observed that the fluid in the manometer rose to a specific height and in the same direction as predicted in our selected problem. This confirmed the expected pressure difference across the system. To ensure continuous flow, the hose pipe was submerged in the bucket so that the returning water remained connected to the flow system. In the first experimental run, the tap was opened only partially, allowing a slower flow rate and a smaller pressure difference. In the second run, the tap was opened even further, producing a higher velocity and a greater rise in the manometer fluid. Flownex was used to create a simulation for our experimental setup. The diameter and height of the bucket along with the lengths of the expanded and contracted pipe sections, were measured and input into the software, together with the respective pipe diameters. Boundary conditions were then set based on our experimental data, including the measured temperature and atmospheric pressure. The pipe friction was assumed ideal and set to the standard value for PVC pipes. The system layout in FlowNext consisted of an inlet tank, connecting pipes, interface nodes, and a reservoir. After running the simulation, the bar graphs displayed at the bottom show how key properties varied from the start to the end of the boundary. The information boxes that appear above each component summarize the applied boundary conditions and calculated parameters. Finally, the results table provides the volumetric flow rate, velocity, pressure, and other important flow properties.